Hello everyone, welcome back to MathGlider. In our first video, we explored different ways of measuring distances, like the Euclidean distance, chessboard distance, taxicab distance, and we also noticed that all these three distances share common fundamental properties, namely positivity, symmetry, and triangle inequality. Today we are going to take these three properties and use them to give a formal definition of what we call a metric. This definition captures the essence of distance in very general way, not just in R2 or R3. So we have a general idea of how we are going to define the metric space. So we will use these three properties. Okay. So we will take a general set. We will call it X or capital M. It is generally denoted by this M symbol. So we will take any general set. Here it is not R2 or R. It can be any set we want. And we will take any two symbol points. And we should be able to define a distance between any 2 points of this space satisfying some properties. Now in this examples we saw that they mainly satisfy property of positivity, symmetry, triangle and equality. So we should take these three properties as a definition for metric space because they are very standard properties when it comes to defining a different kind of distances up till we saw. So we will define the metric space in same manner. So we will define a metric space as a set capital M together with a function which is our distance function. It is from M cross M to R, which means we will take 2 points from M and we will define a distance from M cross M to R. It means the distance will be some real number and we will take in domain 2 points from our sets capital M, and it should satisfy these three properties as we saw: positivity, symmetry, and triangle inequality. So to formally say, we will say for all x, y, z belongs to capital M, which means for all points in our space, in our metric space to be precise. So we will have this three properties, which is positive definiteness, which is similar to positivity we saw, which says distance of xy should be greater than or equal to 0, and distance is 0 if and only if x is equal to y. That means if x is not equal to y, then distance is strictly positive. So we saw it in our three of examples, and we see it comes in metric space definition also. Second property we should take is symmetry, which says distance between x, y is same as distance between y, x. Straightforward to understand. And third property we should have is triangle inequality, which says distance between x, y is less than or equal to distance between x, z plus distance z, y. So this is what triangle inequality, and this satisfies for all of our points x, y, z in M. And then we say this M together with this distance function, we say that it is metric space. So in metric space, what we will have? We will have a set capital M and a distance defined on it satisfying these three properties. Any such pair we will call as metric space. A set along with the metric, a distance function. A metric is what? A distance function satisfying these three common properties. We will call it as metric space. So let us see some examples of metric space. So in yesterday's video, we saw that's where we can say R2 with respect to Euclidean metric is a metric space because it satisfies these three properties. Then we can say R2 with the Chebyshev metric, the chessboard distance. This is also a metric space. And we also can say R2 with the taxicab distance. This is also a metric space now. So three of the examples we already have because of the video, because of the examples we established in first video. Another example is, let us take capital M to be complex numbers. Okay. Now our set is set of complex numbers and distance we will define as absolute value of x minus y. So you know what is this distance? It is simply the distance between 2 points, similar to Euclidean distance. If this is your complex numbers, if you have x and y, these are now complex numbers here, and we will define this distance x minus the absolute value of x minus y is nothing but this line, the length of this line, and it will become a metric space with this distance. The complex number along with this metric is a metric space, we will say. So you know this this usual distance we calculate in complex numbers is a it will satisfy positiveness, positive definiteness property, the symmetry property, and triangle inequality property. So this becomes a example of metric space. Second example we will take is, now we will take our set as an Rn and we will define distance to be the Euclidean metric. As we saw in R2, the Euclidean metric was, the Euclidean distance was x1 minus x2 square plus y1 minus y2 squared and its square root. So similarly, we are defining a Euclidean distance on Rn space. So this can be anything, R3, R4, R5, anything. And we will define the Euclidean metric in similar manner. So here also you can see it will satisfy the positivity property, the symmetry property, and the triangle inequality will also be true here. So Rn with this Euclidean metric, this is also a metric space. So similarly, you can make many such examples like R2 with Euclidean metric. This E signifies the Euclidean metric because we have many such distances. So R3 with Euclidean metric, this is a metric space. So you can construct many such examples. Now in Chebyshev distance, we saw R2 with this, let's say DC is Chebyshev distance. So we saw that this DC was defined in R2 as maximum of absolute value of x1 minus x2 and y1 minus y2. Now we will take our set M to be Rn and we will define the distance little bit differently than Euclidean distance. We will take 2 points x and y. X is the order tuple x1, x2, xn, and y is y1, y2, yn, which are two elements of Rn, and we will define the distance to be maximum out of absolute value of x1 minus y1, x2 minus y2, xn minus yn. So this looks little bit similar to the Chebyshev distance we defined on R2. So this behaves similar to that distance. It is just that in R2 we saw if these 2 points we take, we look at this length and we choose the maximum out of this. But now in Rn we will have more arbitrary things, like we will have R3 and we will look at all the three lines there and we will choose that the maximum out of those lengths. So we will choose like that. So here also you can see it will satisfy the properties positive definiteness, symmetry, as well as triangle inequality. You can check it easily. So this Rn with this max metric, this is also a metric space. Now we will see this little bit different example than Euclidean and maximum metric. So we will take our set to be set of natural numbers and we will define the distance between 2 points x and y to be 0 if x is equal to y and 1 if x is not equal to y. This metric is often called as discrete metric and it can be defined on any set, not only on natural numbers. So we will take the set of natural numbers 1, 2, 3, 4, and so on. Now, with usual metric or we can say Euclidean metric, the distance between 1 and 2 is 1. 1 and 3 is 2. 1 and 4 is 3, and so on. But now, in this discrete metric, the distance between 1 and 1 is 1. 1 and 1 is, sorry, 0. 2 and 2 is 0. 3 and 3 is 0. But 1 and 2, if x is not equal to y, then 1 and 2 is 1. 1 and 3, it is not 2, it is 1. 1 and 4, it is 1. So this is how you define the distance in discrete metric. Between the distance between any two different points is 1 and the point itself is 0. So we will see how it satisfies the three properties which we need. So first of all, let's say positive definiteness. It definitely satisfies because the distance is either 0 if points are same and distance is greater than actually strictly greater than 0 if x is not equal to y. 1 is strictly greater than 0. So it satisfies positivity like that. Symmetry it satisfies because we will take example like the distance between 1 and 4 is 1 and 4 and 1 is 1. So it satisfies symmetry also, that if we take distance between any 2 points, it will be the distance between x y is same as distance between y and x. So it satisfies the symmetry also. And what if we take the triangle inequality property? Let us take three different points, because if we take same points, it automatically satisfies the triangle inequality property. Let us take three different points x, y, z belongs to natural numbers where x is not equal to y is not equal to z. Then distance between x, y is 1. Distance between x, z is 1. Distance between z, y, this is 1. So you can see that if you add these two distances, the distance x, z plus distance between z, y. This is 2, which is greater than or equal to 1. Distance between x, y here. So you can easily see that it satisfies the triangle inequality also. So we will say here that natural numbers, the set of natural numbers with this discrete metric now is a metric space. So we saw this 4 examples of metric space. Okay, first of all, complex numbers, the set of complex number with this your Euclidean metric, and then we saw Rn with respect to this metric. This was also a example of metric space. Then we saw Rn with this metric is also a metric space, and we saw natural numbers with discrete metric is also a metric space. All for today. We defined metric spaces and explored examples like Euclidean distance, Taxicab distance, Chebyshev distance, and the discrete metric. If you found this helpful, don't forget to like the video, subscribe to MathGlider, and share it with your friends preparing for the exam. In next lecture, we will dive right into open balls and neighborhoods. See you there.